In our next line of code, we will try to find accuracy of the best estimator found during the grid search on our testing data. This line of code over here calculates the confusion matrix using the confusion matrix function. This confusion matrix provides information about true positive, true negative, false positive, and false negative values. Um, these predictions are made by the model on the testing data. Y-test over here is a argument in our method which contains the true labels of the testing data, and this next argument over here, which is best estimator.predict function, predicts the labels for the testing data using the best estimator found during the grid search. Later on, best estimator score method calculates and prints the accuracy of the best estimator on the testing data using score method. This accuracy score measures the proportion of correctly classified samples in the testing data. Thus, we will get the accuracy score, which is single value representing the overall accuracy of the model on the testing data. And those four values are true positives, true negatives, false positives, and false negatives that we got for our model's performance. Let's have a look at our next line of code. Now, to plot the decision boundaries and support vectors of the best SVM classifier with the optimized hyperparameters found during the grid search on our testing data, we can use the following code. This code will display a plot showing decision boundaries and support vectors for the best SVM classifier with optimized C and gamma values on the testing data. This visualization is helping us to assess how well the tuned SVM model separates the classes in the testing data. In our next lines of code, over here and over here, we are training two support vector machine classifiers M1 and M2 with different hyperparameters. One is more constrained model, as you can see over here, and the other is more flexible model. This line of code right over here creates an SVM classifier M1 with hyperparameters equal to C, whose value is 1. This regularization parameter controls the trade-off between maximizing the margin and minimizing the classification error. The smaller C value enforces larger margin but allows some misclassification. Kernel used over here is RBF, which is radial basis function, and gamma value is 1. Gamma parameter controls the shape of the decision boundary. A smaller gamma value leads to more flexible decision boundary. The fit function right over here is training the M1 SVM classifier on the training data, X-train and Y-train with the specified hyperparameters. Let's have a look on our next code. Over here, we are training our another SVM classifier which is similar to M1 but has higher gamma value of 50. As you can see over here, gamma value is 50. The higher gamma value can result in more complex and flexible decision boundary. And just like before, over here we are trying to fit X train and Y train with the adjusted hyperparameters over here. By creating and training these two models, we can compare their performance and understand how the choice of hyperparameters affects the flexibility and generalization of the SVM classifier. Typically, a more constrained model will have a larger margin and may generalize better, while a more flexible model M2 can fit the training data more closely but may be prone to overfitting. In our next line of code over here, we are calculating the decision function. scores for both M1 and M2 on our testing data. These scores represent the signed distance of each data point from the decision boundary, and they can be used to assess the model's confidence and their predictions. We can use these scores to analyze and compare the performance of these two models further, or to plot additional evaluation metrics such as ROC curves and precision recall curves. Now, we will use our decision function scores to find out false positive rate, true positive rate, and AUC, which is area under the ROC curve, for both M1 and M2 using the ROC curve and AUC functions. So this lines of code over here calculates the FPR, TPR, and thresholds for different threshold values based on the decision function scores of M1 and M2, which we found out in our last line of code. In these lines of code, we are calculating the AUC for both M1 and M2 using FPR and TPR values obtained from ROC curve function. The AUC provides a single value summarizing the classifier's ability to discriminate between two classes. After running this code, we will have our ROC curves and AUC values for both M1 and M2, which can be used to assess and compare the performance of the two models in terms of their ability to classify the data. Let's learn our next block of code now. In the first line of code, we are creating a single subplot AX with the figure FIG with a specified figure size. In this line of code, this line plot the ROC curves for M1 and M2 on the same axis, and this they are doing using FPR and TPR values obtained earlier. Labels are added to each curve displaying the AUC values for the respective models. This line of over here sets the title of the plot to ROC curves test data. Now we'll see how we can customize the plot. This line adds a diagonal line from 0, 0 to 1, 1 to represent the baseline ROC curve where the classifier's performance is no better than random guessing. This both line sets X label and Y label, which is X axis and Y axis, to describe the axis in terms of false positive rate and true positive rate. And in the last line of code, this line adds a legend to the plot specifying its location in the lower right corner. You can see this is what we get for output for our above lines of code. Thus, after running our above lines of code, we get display of a single plot containing ROC curves for both M1 and M2 SVM models, along with labels, titles, legends to provide clear visualization of their performance in classifying the data. The AUC values in the labels provide a quantitative measure of the model's discrimination abilities. Let's move on to our next line of code. In multi-class classification, we have more than two classes to predict, and each data point can belong to one of those classes. In these lines of code, the first line will display the dimensions of our feature matrix X, which will have the form samples and features. It tells us how many data points we have and how many features a data point has. The second line, which is y.shape, will display the dimensions of our target variable y. Thus, in multi-class classification, the y should be 1D array or list containing the class labels for each data point The length of y should match the number of data points in x. As we can see, it is matching the number of data points in x. Thus, these two lines will help us understand the size and structure of our data set. Moving on to our next line of code. We are trying to generate additional data and labels over here to connect a multi-class classification problem. This first line of code again sets a random seed to ensure reproducibility when generating random data. In our next line of code, this line uses vstack function which vertically stacks our original feature matrix with a new random data matrix of shape 50, 2. This result is a larger feature matrix X that includes both our original data and additional random data. In the next line of code over here, this line of code creates a target variable y by horizontally stacking our original target variable y with a repetition of the value 2 for 50 times. This extends our target variable to include the new class label 2. The last line of this code block adds 4 to the features of all data points in X where the corresponding class label in Y is equal to 2. This operation effectively shifts the data points of class 2 by 4 units along both feature dimensions. As a result, we now have a multi-class classification dataset with three classes 0, 1 and 2. The data points in class 2 have been shifted by 4 units along both feature dimensions, creating a separation between the classes. You can use this dataset to perform multi-class classification using a support vector machine or other classifiers. The next line of code creates a scatter plot of our multi-class classification dataset X with corresponding labels Y. This argument over here represents the values of the first feature x1, whereas the next argument over here represents the values of x2, and c equals to y specifies the color of each point based on the class labels in y. Each class is represented by different colors. As we can see, different colors are used over here. These both lines just names x axis and y axis as x1 and x2. So after running this code, what we get over here is a scatter plot of our multi-class dataset where each data point is represented by a dot and the color of the dot corresponds to its class label. This visualization allows us to visually inspect the distribution of data points and separation between the classes. In this line of code, we will use support vector machine classifier with an RBF kernel to perform multi-class classification on our dataset. After training the model, we want to visualize the decision boundaries and support vectors using plot SVC function. So once we run this code, we will display a plot showing decision boundaries that the SVM has learned to separate the different classes in our dataset. This visualization helps us to assess how well the SVM is performing the multi-class classification task. In our last line of code over here, we are calculating and printing the accuracy of the trained SVM classifier M on the entire dataset X with corresponding labels Y. This accuracy scores measures the proportion of correctly classified samples in the dataset. However, when dealing with multi-class classification, accuracy may not always be most informative metric, especially if the classes are imbalanced. Thus, we now have solid understanding of SVMs, their hyperparameters, and the practical aspects of training and evaluating SVM models in Python. SVMs are powerful tools in a machine learning toolbox, and mastering them opens up opportunity for tackling a wide range of classification and regression challenges.